Good
on?
afternoon.
All right, cool. I will turn this up now because I have to hear the 8 people that are attending virtually.
Good afternoon.
Okay. Okay, so now we can start. All right, so today, I guess I should start with the announcement that I made earlier, which is that as of now, I'm going to make, so we're still going to do the quiz-like structures that I was going to do before, except I'm not going to grade them. Okay, so originally my plan was to give you guys quizzes on Fridays and grade them, but I don't know if you can tell that there's like 15 people who aren't here right now. So I can't spend my entire life doing makeup quizzes, which is what it will turn into. So my plan right now is, what we're doing on Friday is I'm going to write the quiz and hand it out, and I'm going to give you the same period of time we'd have anyway. I'm going to post online. We'll do the quiz so you can test how you're doing in the class. And then after 10 or 15 minutes, where you've had a chance to sit there and work on it, we'll talk about the quiz together as a group, and then we'll move on. So it's going to look like a regular quiz that everyone has an opportunity to take. You can see how you're doing in the class so far. The same rules will still apply to it in terms of if I give it to you in a quiz, it's likely to show up on an exam because I'm trying to give you an idea of the sorts of questions I think are interesting, but I'm not going to collect it and grade it. Okay. Because otherwise I'm just going to end up with like people have like 3 out of 8 quizzes or something, and it's not going to measure anything that way. So that's the first. The quizzes are not going to be graded.
Is the quiz this Friday going to be just over the lessons from this week? Or?
Quiz this week is not going to, so I will post one from last week as well.
Okay.
So I am going to go back and I'll build one for last week, right? This week's is going to be, so this week, the content of the quiz will be 11.3 and 11.4, and I will go back and build one for the previous week, which is 11.1 and 11. Right? And that one I won't be able to do in class until we get a chance to actually do a day where we can collaborate in here together. Okay, that's kind of what I want to do there. Yep.
And then will the quizzes not be graded the entire quarter, or is it just like until?
It's until the quizzes. I won't. So it may be the case that they never get graded. It's a lot, but it's likely if at some point the COVID stuff stabilizes and there's 35 people in here physically again, then I could start running the quizzes for real, right? I mean, because the whole point of the quizzes is not to. The whole point of the quizzes is to keep you guys informed on how you're doing in the class and to give you an idea of the sorts of questions I think are interesting to know how to do. It's not, I don't actually need another component for your grades. I can just double your homework score. That's easy. In fact, for a lot of students, that makes their grades go up. If I put it on homework instead of quiz evaluations. The point of the quizzes is to give you an opportunity to self-assess. So I will make them graded again at some point if it seems feasible. I don't know what the rest of this quarter, I mean, as far as I could tell now, somebody told me this morning that a bunch of people have negative results, but red passes because the IT system hasn't like promulgated the results up into the system yet. So I mean, I'm basically pinned. I can't do anything until everything kind of evens out. Right, so are there more questions about, so that's sort of what I want to do with quizzes. Remember that homework continues to be like the same thing, deal with the homework here. So homework this week that is due, the homework that is due this week is the homework on 11.3 and 11.4. You have access, you will have access, I haven't built it yet, but you'll have access to 11.5 because I'm going to talk about that at some point, probably on Friday. And then remember though that if you don't do your homework and you want it, and the system tells you you're locked out, don't believe it, right? You're not locked out. You just have to request an extension, which is automatic. You'll automatically get it. There's no penalty, and it extends the due date. I don't remember. It's like you get maybe a day from when you request an extension, but you have infinite extensions, at least for 2 weeks, which is the maximum I could feed into the system. And after that, I think I have to grant it manually. But don't get 2 weeks behind. That would be a terrible idea. So this is the homework. All right, any questions about any of this or anything else before I move on to the mathematical content today? Cool, all right. So we're gonna finish up. So last time we talked about the integral test. We're gonna talk today about the second half of section 11.3, which is about using the integral test to estimate the sum of a series. So, which you should be suspicious of, because last time I told you that the value of the integral test and the value of the series were not the same. But we're gonna be doing something slightly different to get these estimates. So to recap, last time what we talked about was, we said that if f is continuous, positive, and decreasing, then, sorry, I guess, and I have a series, so the sum from n equals 1 to infinity of an has an equal to the function f evaluated on integers, then we get this equivalence. This converges whenever this converges. So this is all together, this is called the integral test. So remember that the idea here was, if I have a series that's built out of a function, and that function is continuous, positive, and decreasing, then the series converges precisely when this improper integral converges. Okay. And the argument that we used to do that was sort of this area rectangle type argument, which is going to come up again today. Okay, so how do we test? How do we test to see? I want to make sure I reiterate this. How do we test to see if a function is decreasing? Derivative is negative, right? So this is like a calculus 1 idea. A function is decreasing. I'm going to be really specific here on an interval from a to infinity. If f prime of x is negative for all x in the interval from a to infinity. What we care about here is tail behavior, right? We care asymptotically what happens to the function. It can wiggle around all at once at the beginning as long as eventually it's decreasing. So as long as I can find some point on which the derivative is always negative, then the function is considered to be a decreasing function eventually. Okay? So for example, if you were looking at something like the sum from n equals 1 to infinity of 1 over n squared plus 1. Now we did this problem already. We did this problem, sorry, this one. We did this problem as a telescoping series already, right? We noticed that this was telescoping, we split it up with partial fractions, and we saw that the terms broke up, right? But it's also reasonable to think about this as maybe something that we can hit with the integral test. Right? I mean, you have multiple tools that you can use on a given series. So if I want to use the integral test on this, it's pretty clear that this function has no asymptotes in it, except at 1, right? But actually, this is even defined at 1 and 1. There, now it's defined. But in a 1, I got 0 and 5. That'd be bad. Okay, so this function has got no asymptotes. So f of x is equal to 1 over x squared minus 1 is continuous. To infinity. Positive. Because n squared minus 1, as long as n is bigger than or equal to 1, this is a positive function, right? I mean, if you don't believe me, if you plot it, it's a parabola that crosses through at 1. So that means from this point forward, it's positive. So it is positive from 1 forward. To show that it's decreasing, I just have to be able to compute this. If f of x is 1 over x squared minus 1, f prime of x is it's equal to, and I just have to be able to compute the derivative. Which what's x squared minus 1 to the minus 1 prime, which is going to turn out to be minus 2x squared minus 1 squared. The chain rule. Right? Okay. Now you have to argue that this is negative. Right? That this function is decreasing, which means this must be negative. So is it? Is this a negative quantity for all x past a certain point? Well, the analysis that you have to do, if you've got a problem like this, is you have to tell me. So like say you were writing this problem down and you wanted to know, sorry, I'll bring it up higher on the board here. The analysis that you have to do on a problem like this is you have to tell me why you believe. You can't just say yes and then use the integral test. You got to give some reason why you believe that it's negative. So if you're looking at f prime of x minus 2x over x squared minus 1 squared, and I want to know if that's a negative quantity for some x, and every point beyond, all you have to say is, well, that's always positive, right? Square is always a positive number. So this is always positive. And so really we want to know when that happens. When is the numerator negative? Well, the numerator turns out to be negative whenever x is bigger than 0. Yeah? So this function is a decreasing function. Function decreases. If it decreases for x bigger than 0, certainly it decreases for x 2 and bigger. So the fact that x was negative, but whenever this is true, means that minus 2x over x squared minus 1 is negative for any x in the interval from 2 to infinity. Pick any number in here and plug it in, you're going to get a negative number out. Positive on bottom, negative times a positive is negative. So the whole thing is negative, so the function decreases. So the original f of x is decreasing. And what I emphasize here, the derivative is the tool that we use to discuss if the function is decreasing. And the idea of eventually decreasing. Okay, now from here, if you wanted to use the integral test on this, this is just a setup. We haven't even done the integral test yet. We just said we're allowed to. All this work was just to say we're allowed to use the integral test on this function. Not that we've actually tested the series for convergence yet. Okay, so we've met the properties that we need to apply the integral test. Now we actually have to do the integral test. So what is that's going to be rough. It actually, so you can do this with trig integration. You can, or you can do it with partial fractions. This is actually easier with partial fractions than it is with trig, because the same thing in this context, you should identify this immediately as something you should use partial fractions on. In the series setup, so if you see it in this form, it's not immediately apparent in a series form that this is something that partial fractions will turn into a telescoping series, right? But we spent a lot of time in calculus 2 talking about integrals of rational functions. And anytime you see a rational function and it's not immediately a trig function, I mean, you could use an arcsecant here, or you could rewrite this as the integral from 2 to infinity of 1/2 of x squared minus x minus 1 minus 1/2 of x. Use partial fractions to split this into these. Now, I didn't do that step for you because I'm going to presume everybody can do this at this point. That you can take a function in this form and factor it into its, so this is partial fractions. And when you're done with this, it's going to turn out to be the case that the limit of this thing is finite. In fact, I think it's e, or 0. Right? All that matters is that it's finite. So you go through you go through the standard improper integral. You will have to use the fact that the natural log of a minus the natural log of b is equal to the natural log of a over b. You're definitely going to want to do that in this problem because it's going to make the limit way easier. And when you're done, you're going to find out that this is bounded. So this is what I want you to do is the reason I haven't done the details here is these are calculus 2 ideas, and you should try this integral. You should try to see if you can prove that this series converges using the integral test. This is a good example of a problem where this technique works. And your hint is you should do that because you're going to get an infinity minus infinity, which is indeterminate. Okay. Right, so this is an exercise. Good practice. You already know this series converges because we did with Kelso. Okay, questions about that? I just wanted to get another one of these down, like an integral test example before I go to estimating the sum. Okay. So now we're going to talk about estimating. Sum of the series. And in particular, estimating sums of series where the integral test applies. Right. So again, continuous, decreasing, positive functions here. And the basic observation is if a series converges, so suppose that this converges to a limit, we'll call that limit S. So it adds up, and the number it adds up to is the number S. We know that Sn, which remember is the sequence of partial sums, the limit of that sequence is S, right? As I keep adding more terms, I'm going to get closer and closer and closer to S. So taking the limit of the Sn's gets me S. Does that make sense? The limit of the sequence of partial sums is what the series adds up to. Every time I write S, you should think in your head, oh, it's this. It's the whole series. More terms added on means closer to S. How close am I? So what we can say is for a given Sn, so pick an n. Pick some number of terms. 10, 20, 30, 100. Sn is equal to S. Well, actually, let's do this. How close am I? We'll do it this way. Well, S is what the whole series adds up to. My approximation is Sn, and Sn is never going to be exactly equal, right? Because I keep putting more and more stuff into here. So the difference between where the limit actually gets to and my partial sums, we're going to call R of n. This is the remainder. So you can think here, another way of writing this, if I wanted to use sigma notation, would be the remainder after estimating by n terms is the whole sum minus this part of it. Oh, I gotta be careful here because I'm doubling up my index. Oh, okay. The remainder is the entire series, and then take out that first partial sum that I'm estimating it with. This is my guess. This is the actual value. So the error or difference or remainder is the whole sum minus the part that I've tried to estimate it with. That make sense? Okay. So this is, you can think of as being the error of the estimate. Okay. So that means that we can write down, so what is Rn actually? So Rn, well, if Rn is A1 plus A2 plus A3 forever, minus A1 plus A2 up to an. So the remainder is the whole series minus the first n terms. Get every term after the first n terms. Okay. So the remainder is everything that's left over in the series after you take out your guess, your approximation. And the remainder is the thing we can control with the integral test. So I can control the size of the remainder with the integral test because, and here we're going to use that same rectangle trick from last time, because now that I've got totally chalk. We're going to use that same idea of thinking about this series as a set of rectangles. So you can imagine somewhere out here is n plus 1. And there's this function f of x. Here's f of x. Now, the area of these guys, if I think about this as the area of rectangles, I have two different ways to think about them. I mean, an plus 1 means that we have this rectangle right here, right? So there, that is an plus 1. This rectangle right here has width 1 and height f of n plus 1 is equals, yeah? The height of this rectangle is just the value of the sequence at n plus 1. So the area of this is an plus 1. And the area of this is an plus 2. And the area of this is an plus 3. Because the height of that rectangle is an plus 3. The height of this rectangle is an plus 2. The height of this rectangle is an plus 1. So notice then, what this graph is supposed to imply is that the remainder term must be smaller than the integral from n to infinity of f of x. The area underneath all of this contains all of the areas of these rectangles, and so it must dominate it. So this is a way of getting an approximation for how much I missed by. At worst, the amount my approximation is off is at most this. And this is going to tend to be really tiny. Okay. So there's one approximation. Well, but there's another way of looking at this, which is I can think of it as an overestimate. So if I look at the same picture, but I switch where the rectangles are, I can draw this picture. So now start the function right here. At n plus 1 instead of at n. This again, this about the value of this is f of n plus 1, which is a n plus 1. This is f of n plus 2, which is a n plus 2, and so on. Now what happens if we put the rectangles up here? Well, this thing is still has height n plus a n plus 1, and width 1. And the area of that big rectangle is an plus 1. And the area of this rectangle is an plus 2, because the height of that rectangle is an plus 2. What that means is, whatever my error estimate is, it's bigger than this area contained in here. So what this picture is supposed to show you is that an plus 1 plus an plus 2 Rn is bigger than the integral from n plus 1 to infinity of x dx, which tells you the least my error could be is also controlled by the integral test. I have to start here. If I'm sliding the rectangles to the right, so I have to start my integral over here and get this overestimate. So altogether, what this shows, the reason that I'm showing you the geometry here is to give you the idea that we really are just manipulating the fact that we understand how integrals work to say that the error in approximating S by Sn is Rn, but which is strictly trapped between, or which is trapped between the integral from n to infinity of fx and the integral from n plus 1 to infinity of fx. And that gives you pretty tight error bounds in a lot of cases, right? This gives you a way of controlling precisely how many terms you need to get an error to the tolerance you want. And that's one of the big ideas of scientific computing, is to be able to say not just, well, I know Sn approximates n, right? That estimates the sum. I take 10 terms, I'm just going to say that taking n equals 10 gives me a reasonable approximation by series. This tells you how good that approximation is. And it also gives you a way of pre-specifying what your tolerance is and finding the right number of terms. So you have control over the estimate. And this is kind of jarring, maybe if you haven't seen calculus used in a numerical way, but this is the way calculus actually used in practice, right? These ideas from calculus are used hardly ever as anybody integrating an indeterminate function in the real world, but almost everybody has to work with these kinds of estimates. They give you some idea of, if I want to approximate a quantity by a piece of an infinite sum, how far do I need to go to get it within 0.0001? 0.000001, right? Whatever your tolerance happens to be. All right. So let me give you a concrete example of what this looks like. Oh, here's a good one. Okay. So I'm going to follow the example in the textbook. This is example 5, and it says approximate the sum of 1 over n to the third with 10 terms. And it wants to know how good the approximation is. So S10, 1 over 1 cubed, 1 over 2 cubed, 1 over 10 cubed. If you put that in a calculator, what you're going to end up is a number about equal to 1.91975. And that's awesome, except, again, whenever you're approximating in the real world, when you're doing computational mathematics, you have to know not just what the approximation is, but how good it is. It's not enough just to know an approximation. You need to know the error bars on your approximation. So what are the error bars going to be? Well, you can compute R10. So R10 you cannot compute because R10 is equal to all of the rest of the series, but it's the error. R10 is the error. And whatever that error happens to be, it's less than or equal to the integral from 10 to infinity of 1 over x to the third dx. And that's an integral that can be attacked. In fact, this is, you can just write this out. This turns out to be 1/200. So how many digits of precision did I get out of this particular estimate? Or 1/200. What's this? What's the last stable digit in my estimate? If my error is smaller than 1 over 200, where's my last stable digit here? How many significant figures do I have? I know I'm pushing a little bit, but would you trust the 1? Yeah, because that's on the order of a 10. You trust the 9? The 9, to move the 9, you'd have to have an error that was larger than 1/100, right? 1/100 up, 1/100 down. This says the error is smaller than 1/200. So that's, you can think about this as being a stable quantity. This, past this point, you can't trust your approximation. The idea here is having a measure of how good your error is tells you how much of your approximation you can trust as significant figure. And then more broadly, I mean, I don't want to, I'm not going to spend a ton of time doing a bunch of examples of these, but I really want you to be able to understand that in practice, the way we do a lot of stuff with series is this kind of approximation. Okay. So the upshot is this kind of approach, like they took in exercise 5, where you get an idea of how good your approximation is, leads to a set of inequalities that says precisely how good your guess is. So in terms of n, this number is equal to the number of terms. Number of terms in the approximation. You get this nice formula that says that whatever your actual value is, it's trapped between the nth partial sum and this integral. And this one. So this infinite thing that you can't compute, you can compute to basically whatever precision you want by this formula right here. The way these things get used in practice is you just tune this, where you let n run to some quantity that lets your estimate stabilize. So approximation plus under error is less than or equal to actual value, which is less than or equal to the same approximation plus an over error. And that lets you get a really tight window where your approximation can actually live. Okay. So these sorts of approximations are a core of basically using calculus in science. Now, I'm not a numerical guy, I'm not a scientist, but I know that your calculus-based courses, you end up doing a lot of this stuff as you go on in your science classes. A lot of these kinds of methods where you are approximating these quantities that are continuous quantities, but with these discrete approximations. And so as dry as that might seem, this is a really important idea. Okay. Now, can I test you on this idea? Probably not. I have to come up with some way of doing it without making you do it with a calculator. So anyway, okay. So what I want you to take away from this conversation is that infinite sums can be approximated by partial sums, and also that they can be approximated by partial sums in a way that you understand how bad the error is. Try to move on to something more enlightening or mathematically pure in a second. Are there questions about this? Okay, so let's go on to my favorite, one of my favorite sections of this book, of this chapter, which is the comparison test. And we've already seen some of the comparison tests. We're going to start with a real brief introduction to 11.4. All right, so comparison tests. Comparison tests. The comparison tests are awesome because it means you can use existing knowledge, usually the convergence of P series, to predict whether other series are going to converge. So this is about using existing knowledge gain information about P series. The last time we talked about this, or the series in particular we talked about, I think we talked about 1 over n squared. Sum of 1 over n squared plus 1. And I'm trying to get you guys to think qualitatively about whether or not a series converges or not, right? So when you look at that, Does anybody remember what the argument is here that this should be a convergent series? Why should this converge? Besides the fact that you know by the integral test it integrates the arctangent. Forget that. Suppose you didn't know the integral test. Somebody just plopped that down in front of you and said, should that converge?
Can you compare it to one over n squared?
Why does 1 over n squared converge?
Because these two series.
Ah. So one of the things we have to keep in mind is what sort of things converge, right? We got to have a library of convergent series. So over here, we're going to store up the idea of P series, the most important series in this study. Remember, have the form 1 over n to the P, and they converge. And P is bigger than 1. Okay. So I look at that. And yeah, I think last time what we said, we sort of eyeballed it and said, well, it kind of looks like 1 over n squared, because what's the plus 1 doing? Right? When n gets enormous, the plus 1 doesn't really do much. A billion squared plus 1 and a billion squared are basically the same number. So you say, okay, well, it's kind of like, it's not really a mathematical symbol, kind of like the sum of 1 over n squared. See, I'm not being rigorous right now. I'm just saying you're guessing, right? You're just guessing. It looks like 1 over n squared. That converges. Kind of looks like 1 over n squared. So maybe that also converges. It should converge. It acts the same. That's the whole point of the comparison test, is to say the things that look the same should act the same. So a more formal way of looking at something like the relationship between this series and this one would be to do the following. Just write down some partial sums here, or some terms. If you had 1 over n, 1 over n squared, and 1 over n squared plus 1, then notice that the terms here look like 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on. And the terms down here now everything in this problem is positive, and that's really important. Nothing's flopping around, there's no negative signs, there's no alternation going on. We just have this. And if I cut this off at any finite point, I'm going to just cut it off. There, I've got the fourth partial sum. Notice that every single term, what's bigger, by the way? N, 1 over n squared or 1 over n squared plus 1? 1 over n squared is bigger because n squared is smaller number. You can do this directly if you want. N squared is smaller than n squared plus 1. So 1 over n squared is larger than 1 over n squared plus 1. It's the inverse relationship, right? The larger the denominator, the smaller the number. So that means that this is bigger than that. This is bigger than that. And this is bigger than that. And this is bigger than that. And that will be true for any finite sum at all, right? I could cut this series off everywhere, and each pair of terms are going to have this relationship. This quantity will always be smaller than its corresponding quantity in this series. What that means is any partial sum here, Sn, is going to be bigger than any partial sum down here. Maybe I call it sigma n. There we go. It's like an S, right? So here what I mean is, this is the sum from k equals 1 to n of 1 over k squared. And this is the sum from k equals 1 to n of 1 over n squared plus 1. No matter where you fix the partial sum, these always have to be bigger than these because each term is bigger. If this is bigger than that, and this is bigger than that, and this is bigger than that, and this is bigger than that, if I add them up, adding up a bunch of bigger stuff stays bigger than adding up a bunch of smaller stuff. So for any n, this statement holds. And since it holds for all n, we say this. So this is true for any n. And so we say, oh, well, then it must also be true once we use the notation that means that we're taking a limit. That converges. This converges because it's a P series. And smaller than something finite is finite. So because this sum is smaller than that one, this sum is smaller than infinity, this must also be smaller than infinity by the transitive property. It's important all the terms are positive here. The monotone convergence theorem doesn't apply. So we conclude that this sum converges. And that's the core of what we call the comparison test. The comparison test requires that we have something to compare to that we know how it behaves. So I'm comparing 1 over n squared plus 1 to 1 over n squared and saying, well, 1 over n squared is smaller than 1 over n squared. 1 over n squared plus 1 is smaller than 1 over n squared. So because this converges and this is smaller, that must also converge. So formally, we write this as follows. Suppose sum of an and sum of bn series. And this is very important with positive terms. Okay. Required that things have a positive term. Then one. The sum, let's say if the sum of Bn is convergent and An is less than or equal to Bn for all n. So if I've got a convergent series and I've got another series whose terms are all smaller than the terms of that series, then the sum of the an's converge. If I have a convergent series and I'm smaller than that, then the smaller series also converges. Smaller than finite means finite. We can use it in the other direction. So statement 2 says that if the sum of the bn's diverge, you have a divergent series, and it can only diverge to infinity because everything is positive. If the bn's diverge, and I've got some terms that are larger than the terms of that series, larger than infinite is infinite. And the sum, the an's diverge. Okay. Now this lets us attack some truly weird series. Here's an example. Sort of stuff that that gets done here. So let me not so much this 1 over n squared thing, but I could write a series like this. So when you're looking at a series, you want to make sure that you hit it with your whole tool belt to figure out what the appropriate test to use on that series is. So I look at this and I say, does that converge or diverge, right? So the problem might say something like, determine the convergence of this series. Determine convergence. And you look at it and you say, okay, well, what are the tools we've got at this point? Does it telescope? The answer is probably not, right? There's no partial fractions here. It does not look like an obvious way to break this thing up. So no. Is it geometric? And the answer is clearly not, right? I mean, there's a cosine running around inside of it. It's not a to the r, ar to the n minus 1, so it's not geometric. Can I integrate this function? I don't know how to integrate cosine squared of x over x squared. The third question is, can I integrate the integral cosine squared of x over x squared dx? And the answer is nope. Not last time I checked, I can't do that. So if you can't telescope it, it's not geometric, and you can't integrate it, the next tool we have in our file is the comparison test. So the next question is, does it look like a p-series? And the answer is almost, right? Almost looks like a p-series. There's a p-series piece right here. So the observation you need to make is, damn, it would be cool. So if this is going to be convergent, it's going to converge because it looks like 1 over n squared. So the answer is yes, sort of. It sort of looks like a p-series. So what I want to know is, if it was going to be convergent, using the comparison test, this should be true. If that statement was true, and we don't know, if that statement was true, then the fact that this converged would force that to be convergent. Is that true? So now the reason I picked this particular question is so I could introduce you to one of the math book's favorite inequalities of all time. What is the range of cosine? What's the range of the cosine function?
-1 to 1.
-1 to 1. What's the range of a cosine squared? 0 to 1. So whatever cosine does, it can't ever get above 1, right? It can't. It's impossible for cosine to go above 1. So here is one of your textbook's favorite inequalities. So this is one of these textbook. It's not just textbook. It shows up all the time in practice too. So this is a textbook inequality, which is used to create hard-looking homework problems out of easy ones. Since the cosine can never get above 1, cosine squared of x is always less than or equal to 1. That's just a true inequality. True statement. You guys may have seen this before in the forum. So sometimes that looks like this. The absolute value of the cosine of x is less than 1. This is another version of that inequality that we will be using. Okay. Cosine of x is a bounded function. Cosine squared is always positive. It's less than or equal to 1. So what that means is that this statement is true. That inequality is true because you can divide both sides of this by n squared. And so since this inequality is true, we would say, because, here's basically how an answer to this question would look like. Since cosine squared of n over n squared is less than or equal to 1 over n squared for all n, and the sum of 1 over n squared is a convergent p-series, the sum of cosine squared of n over n squared converges by the comparison test. Every piece of that answer is required to be there when you write these things up. So when you're telling me that a series converges by a particular test, you have to show me that you understand what all the hypotheses are. You have to identify the test you used, identify the result of the test, and make sure that you understand that these are the hypotheses of the comparison test. You've shown me that the terms satisfy an inequality, and you've showed me that you understand that this thing is convergent and the reason why it's convergent. Okay, so you don't want to say, determine the convergence of this series, then you write down convergence, which is, yes, but if I don't have any work, I can't see why you believe that. Okay? But that's it. Now, the wrinkle that I'm going to throw into the comparison test here is it's really easy to break it. This is the last thing I want to say before I let you guys go, which is, what if I have a series that looks like 1 over n squared minus n minus 2? What's the problem? How does that compare to 1 over n squared? I mean, in the limit, you should look at this and say, whatever this does, it should be the same as that, because when n gets gigantic, this looks like n squared, right? What's in which direction is the inequality point? That quantity is small, this quantity right here is smaller than n squared, right? Because I've subtracted things from n squared. So this is smaller. 1 over something smaller is bigger. And bigger than a convergent series doesn't tell you anything. So I've broken this problem by making a series that's basically a p series with p equal to 2, but I've got the inequality point wrong. So we're going to have to fix the comparison test with some beefed up machinery to take care of this, because when you eyeball this, I mean, so the comparison test says nothing. But you want it to, because it still looks like a p series with p equals 2. And that's why we're going to get the limit comparison test, which we'll talk about next time. We'll do another example of comparison test. We'll talk about the limit comparison test, which will let us pick up series that have that sort of form. All right. Thanks for coming. I'll post this video when I'm done, and talk to you guys soon. Bye, guys.